Yes, sir.
Okay, so this is the general form of difference equation. Actually, you know that in a discrete time system, the input-output relationship will take the form of difference equation. This is simply taking the difference of two output at two sample points that will give you the difference of your output. So in this way, depending on the system behavior, your input-output relationship will be determined. But for a single input and output system, the equation will take this general form. Your yn plus 1. Okay, I prepared this lecture from BP Lati's book. So one thing I need to mention that some notational differences are there. In your BP Lati's book, K is used as a sample point. In our Heikin's book, it is N. Okay, those two things are same. Another issue is that here the input is represented by xn, but in BP Lati's book, your input is represented by fk. Okay, all are synonymous. So what you need to do, you have to concentrate on the underlying technique that is used to solve those equations. Now your first one is, we call it advanced operator form. Your second one is delayed operator form. In both the forms, we can proceed. Okay, let us proceed with solving the equation, because this equation you see very numerical and they involve only addition, multiplication, nothing more than this. So our objective is we have to solve for yn. If we want to find yn, okay, the n for a causal system, your yn will be from n equal to 0 to in the positive direction. So you can set the value of n equal to 0 there, that will give you y0. So you plot your y0 in the same way we calculate your y1, y3, etc. Now if we examine both of this equation, you see that if we put in the equation in this form, or you can put in this equation, then our objective is what we need to find, for example, yn for different values of n. So if you want to find yn for different values of n, in the same way yn for different values of n, here you need some values from your previous state. For example, for n equal to 0, you will need y minus 1. Similarly, in the next step, you will need y minus 2, etc. Okay, can you mute noise? Some noise is coming.
Hey, Sumaya, mute yourself.
So what you can do, if you want to find, for example, y0 in this equation, you put your n equal to 0. But in the advanced operator form, you have to put, if you want to find y n0, then what will happen then? You have to put n equal to minus n, capital N, then you will get y0. But
Yes,
in all the cases, what you need to know, in order to calculate your present values, you may need some few past values. Those will come as initial values. But for your subsequent calculation, for example, if you want to calculate y1, then you see that you will need y0, isn't it?
yes, sir.
Your y0 will be coming from your first step. In the same way, if you want to calculate y2, your y1 will be involved there. So in this way, by using iterative technique, you can solve these equations. This is very simple, but not efficient. The reason is that if you have your many numbers of samples in your input, or you have the order of your difference equation is higher, then what will happen, you need more time to calculate it. But still you can use it in some limited sense. But then what you need to do then, we need to explore for what you call, even your differential equation can also be solved in this way very simply. Okay, I will show you later. Okay, that how a differential equation can also be solved by a very simple addition or multiplication technique. And some of the standard algorithm for solving differential equation you have already known in your numerical analysis course.
Yes, sir.
Okay. So in order to proceed with what, okay, this is what the iterative technique just applied. You can verify it, no problem. But we will be going to find the general perspective that how can we solve the difference equation in a closed form so that we can calculate the output for any values of n. In order to do that, like your differential equation representation using operator form, the same technique will be used here. So you see that in our case, the output samples either advanced or delayed, same is true for your input samples. So in this case, we can use the number of samples in your input lecture from BP Lasse's book, where E is used as the operator in difference equation. So in general, it will have an exponent that signifies what we call the order or the number of sample it will be delayed. For instance, okay, if we write yn e to the e exponent n yk, this is not multiplication. We are saying that yk is being operated by this operator. It will result advance of your output in this way, k plus n. And if it
Yes,
is
sir.
plus or minus, it will be plus and
Minus.
minus. Okay, yeah. So your minus will be represented by minus exponent, plus will be represented by plus exponent. So having this thing with us, we can easily represent our general form into a polynomial form of operators, something like this. You see, our first term was what? Our first term was say y. This is a problem. Our first term is y say k plus n. If it is yk plus n, then that yk plus n is equal to e exponent n yk, isn't it? So this is what that term.
Yes, sir.
Similarly, your y next term will be equal to yn minus 1. So it will be equal to this. In this way, we can have a polynomial of operators in the output side can be written in this form. It is very similar to D operators that we used in differential equation. So yeah, this is your input side and this is your output side. Okay, just following the same notational procedure that has been followed in
Previous class.
solving differential. Yeah, we can represent our input operator by QE, output operator by QE, and input operator by PE.
PE.
So this is, yes, this is what the simple or short or brief representation of a difference equation. Okay. Now the thing is that how to proceed with the solution. Once we have this equation with us for a particular system, our step will be what? We have to find yk, the solution of the output. Then you know that your yk has two parts. One we call YZIR, that means zero input response, isn't it?
Yes, sir.
And another part is
Z, sir.
YZSR. Okay. Now, this solution technique of representing our output is the generic technique that we usually use in signal science systems. But mathematically, that yk can be solved without splitting these two responses. Okay, this is what the classical technique you have already learned for the case of ODE. That the solution of a differential equation will have two parts. One is called complementary solution, and another is particular integral. Okay, again we can separate it into two parts. One called homogeneous solution, another is a forced response. Okay,
Yes, sir.
so now the thing is that from the homogeneous part or natural solution, we usually obtain the YZSR. So in order to obtain YZSR, what we need to do, we have to put our input equal to 0. So if we put that input here, in this case, input is Fk. If we put input equal to 0, then that equation would be equal to 0. And we are, in this book, this solution is represented by Y0K. So your Y0K is the natural response of your homogeneous solution of your difference equation. Then how to solve Y0? The same technique. You can solve Y0 by using your recursive technique, or you can solve your Y0 by uh, an analytical technique. But we have some logic of selecting the standard solution. The reason is actually coming from the physical explanation. You know that the YZHR is actually due to what? Due to the previous initial values of your system, isn't it?
Yes, sir.
And you know that if you do not feed anything to your system new, and your system has some initial values, you are using it, then what will happen? In general, for a real system, that output will not continue forever. After some time, it will be gradually decaying out, isn't it?
Yes, sir.
For example, if you have some money in your bank, you are not putting any additional money to it, and your bank also not giving any interest to you, and you are every month you are taking withdrawing money. So what will happen? Will your money be there in the bank account forever?
No, sir.
It will be depleted and consumed. Okay, that the same thing, that if you do not put any input to our system, that your system cannot sustain its input unless we there, because real system will have some element there that will consume the energy in every run. But some special case is there that we discussed earlier for a second order system, that if you have some oscillatory energy storage element there and no dissipating element is there, energy dissipating element, then what will happen? Once some sort of energy is given to any one of the elements or both, then an energy exchange will be occurring between them, and that will continue forever, isn't it?
Yes, sir.
And physically, will it happen?
No, sir.
No, it is something like that perpetual type motion. Okay, for example, say if we have a mass and you are putting a mass over a plane that doesn't have any friction, and if we put a force to it and it will begin to move, then when we withdraw our force, will it stop?
No, sir.
What will happen? It will move for, keep going on moving, isn't it?
Yes, sir.
Because you see the equation become, you know the equation. Don't you know the equation, Newton third law or Newton second law, isn't it?
Yes, sir.
What is it?
F equal to ma, summation of F equal to ma.
Okay, if it is your summation of m, for example, say it is force is equal to ma, isn't it? Actually, this can be written as m into rate of change of velocity, or you can write it m into velocity is the rate of change of displacement, isn't it?
Yes, sir.
Now you see that your velocity, some initial velocity was there in your system. Okay, consider that your system was moving from the rest in a frictionless surface, and then you withdraw that force. Then your equation will be equal to what? Okay, let me share, because this is very interesting, something you need to know. Okay, let me share the whiteboard then, because although it is not that much connected with, of course connected, but not, but you have to know the connection actually, how they are connected. Okay, then you see that in your mechanical case, your equation for your ZSR for a simple mass can be m dv by dx or equal to dv by dt equal to 0, or equivalently m d2v d2x dt2 equal to 0. Okay, this equation will be meaningful only when some initial velocity exists, isn't it?
Yes, sir.
Because if you solve it, what will happen? Your velocity would be equal to what? Your velocity would be equal to constant, isn't it?
Yes, sir.
If your velocity is constant, then your displacement to x would be equal to what? C multiplied by t plus another constant, isn't it?
Yes, sir.
And some mass will be there because if it is m dv by dt equal to constant, isn't it?
Yes, sir.
If we integrate this equation first, you got the point.
Yes, sir.
If we integrate this equation once, then it is what? M dv by dt.
Yes, sir. Yes, sir.
Then if you again integrate it, then what will have no. What is that? Because this is the no. If we integrate this equation first,
One square will disappear.
then that means it will be equal to,
Dx by dt.
it will be equal to m dx by dt equal to, say it is a constant. Okay.
Yes, sir.
Next thing is what? Your m dx by dt would be equal to what then? Equal to c
M.
by m, isn't it?
Yes,
Then
sir.
x equal to what? C by mt into, say, another constant d, isn't it?
Yes, sir.
Okay. So you see that it is C is the thing that is actually initiating that displacement. What is that C? C is related to initial velocity, isn't it?
Yes, sir.
Because this quantity is your initial velocity. So if you have our initial velocity present in a frictionless surface, then you see that your displacement is occurring in this way. Can you plot it? You see that it can have a displacement at t equal to 0. Say this is d. Then it will follow a straight line, something like this, isn't it?
Yes, sir.
That's why when your time is going, it is moving. So its movement will stop.
When a force will be applied.
No force is there. Unless you apply a force there from opposite end, will it stop?
No, sir.
It will not stop. Okay, it become unstoppable. Have you seen a movie Unstoppable?
No, sir.
No, none of you. About, we have our 92 students there.
Sir, I saw, sir.
You saw, what is it?
Sir, it's about a train, sir.
It's about a train. Okay, when a train has failed its brake and it cannot be stopped, then it has been stopped by putting by a train from opposite direction, isn't it?
Yes,
But
sir.
that didn't work, sir.
Yeah,
But that didn't work.
that didn't work.
Yes, sir.
Okay.
Later, they had to lose the every partition of the train, and
Okay.
it will lose
So
the
this is
speed.
how it becomes unstoppable. Okay, if you put in this way. So and can you give me an example of the similar system in electrical? It is simple. Okay, anything that has this type of derivative current through your inductor or voltage across your capacitor will have the same nature, isn't it?
Yes, sir.
You see that if you want to use it, this equation equal to 0, you will see that still you have a current di that is a constant current. Okay, that means this current is constant. If your current is constant, then your charge will be increasing to infinity. Otherwise, constant current cannot be maintained, isn't
Yes, sir.
it?
Yes, sir.
So this is how this system actually in practice doesn't exist. We have a friction as a result. The initial value, for example, this equation can be modified by a frictional term. When a frictional term will present, that friction will consume the energy and eventually your mass will stop and current flowing through your inductive circuit also ceases. So that is not the case. So in practice, what is happening? Your system will not be perpetual. Okay, your system will have some sort of what we call resistance that will or friction or any energy consuming element that will consume energy. With
Yes,
this
sir.
thing, what we have obtained, we have obtained that for the homogeneous solution or natural solution ynt in the case of continuous time, it takes a general form e to the power lambda t, isn't it? And that particular thing is the characteristic root. Depending on the order of your system, the number of root will be there. For a stable system, your lambda will have at real value negative, isn't it? Or for a higher order
Yes,
system,
sir.
if it is complex, conjugate, then real part should be negative. But we have situation when some real part becomes positive, then your system become unstable, okay?
Yes, sir.
But if your system is unstable, still we have some technique to bring it to the stable region, and I hope you will learn it more elaborately in your control course. So with this thing of characteristic nature of our natural solution, same logic will be true for our discrete time case. If we set this side equal to 0, then we are calling this response y0k. Then your y0k must have a solution very similar to the natural response of your continuous time system. Usually it is written as some constant into say gamma to the power say n. This will be the nature of solution, homogeneous solution for your discrete time system. Okay. Now we have to explain what is it. Actually, you see that C is the constant that will be determined. We'll explain it later, but only characteristic factor is gamma. Okay, this factor will determine the nature of the response of your y0k. But tell me now then, for a lossy type practical what we call discrete time system, what restriction should be there on your gamma? In a way, what have we discussed in the case of continuous time system, that the restriction is a real part or the real value of the characteristic root must be negative for a stable system. So can you identify the restrictions on gamma for stability?
So it should be from 0 to 1.
That means it must be less than 1. Okay, if it is not if it is 1, then it will be remaining constant. So it must be less than 1. If it is greater than 1, then what will happen? As we have an exponent there,
The system will
as
be
your
unstable.
time grows, system will be unstable. Very good. So our objective here is then we have to solve this characteristic value gamma for our discrete time system, and it is not very difficult to be understood. What we can do then, just you simply set the right hand side of this equation equal to 0, right hand side of this equation equal to 0, then this solution will be equal to y0. Then this is what your equations for obtaining natural solution or zero input response or homogeneous solution in whatever way you can call. Now, in this equation, as we assumed that the solution will y0k will take this form C into gamma power k, then we can put this solution to this equation and we will obtain the characteristic equation of this difference equation like differential equation. After inserting the homogeneous solution to the differential equation, we obtain the characteristic equation. In the same way, we will obtain the characteristic equation for our difference equation. Okay, look at this slide. This is what our equation. Then we assume that our solution is of this type. Then that you replace your y0n by this value. Then what will happen? This y0k is being operated by the operators. Okay. So in this way, the operator will operate your solution. For example, EY0K will be equal to Y0K plus 1. So your Y0 is C gamma power K plus 1. So you replace your K by K plus 1. So this is your EY0K. You can write it in this way. C into gamma power K into gamma. Can we write it?
Yes, sir.
Yes, sir.
So if we operate it twice, then you will see that this is equal to this should be equal to then C gamma power K into gamma square, isn't it?
Yes, sir.
In this way, this would be equal to C gamma power K gamma n, isn't it?
Yes, sir.
So all you put this thing there in this equation. Then you just rearrange the equation in this way. You see that gamma k is there in all of your parts. You can take it as a common factor. Your constant is there. Then you see in this equation, C gamma power k cannot be equal to 0, isn't it?
Yes, sir.
If it cannot be equal to 0, then this polynomial of gamma would be equal to 0. Okay? And n is the order of your system. So if you have our n known to us and the constant associated with the gammas are with us, then it will be a simple equation, isn't it? And that order of the equation depends on the order of your system. Okay, then we can solve this equation to find the value of gamma. Once your gamma is available, then your solution will be available, but constants will be there. Those constants should be determined from the initial values of your system. Okay, this is what the whole process. Now, like your continuous time system, the characteristic root lambda for continuous time system has some behavior that we need to investigate, because based on this behavior, the nature of the response should be identified, whether it is damped, underdamped, overdamped, or undamped, isn't it? In the same way, we can also categorize the response of a discrete time system by examining the root of this characteristic equation. Let us see what are the possibilities, although the things are not new to you, but still we can revisit. So the root of this equation can be distinct. Distinct means they are what to call separate. They're okay, but they can be negative, positive, we don't know, but they are distinct. If they are distinct, then the solution yk can be written as a linear combination of these distinct roots, isn't it?
Yes, sir.
Yes, sir.
Okay. So this will be the solution then for your yn y0k. Then you see that we have our c's there constant that you need to determine. Just you follow your initial conditions there. That will help you to find the value of. For example, if we have two unknowns constant, we need two initial values here, and depending on the order of your system, your initial value will be available. Now we have another situation where you sum of the roots of that polynomial can be repeating and others are distinct. In your differential equation solution, if we have, for example, a differential equation that's consider that is giving you a factor, say giving you a factor, say lambda minus 1 square equal to 0. How many roots are there?
Roots.
Two roots, isn't it? That means you have two roots, but both roots had the value equal to what?
Yes, sir.
Then lambda equal to 1, but it has two roots, isn't it?
Yes, sir.
Now, how to write the solution then? Because if it is distinct, then we can write the solution, say a into e to the power
So
lambda
one
1
term will
t
be multiplied by
plus
2.
b into e to the power lambda 2 t. But in this case, you cannot write this thing. Can you write?
No,
No,
sir.
sir.
Then how to modify?
Sir, A plus it
A plus t into
A. Wait,
Yes, sir.
a into e to the power
minus.
lambda t, isn't it?
Yes, sir.
Another concept. You know this thing, okay? That means you have to put another thing there. This is the nature of what we call overdamped system, isn't it?
Yes, sir.
When the roots are equal, is negative, then your system will be overdamped type. No. Is it overdamped or critically damped?
Critically damped, sir.
Yes, critically damped. So you know the system, okay? This is not new to you. Very good. So in this way, what will happen then? If you have your two root, then two term will be there, t. If you have your three root, then another term t square will come. That means the square t term that is coming in your solution will be order will be what? One order less than the number of root, isn't it? So in the same way, if we have our discrete time system characteristic root repeating, say r times, then your solution can be written in this way, okay? Instead of t, our variable is n or k. In this text, it is k, but if you go to your Huygens book, it is n, okay? That means number of samples, that is what our variable. So this is what the thing. So this will be the solution part for repeating root of lambda 1, because lambda 1 is repeated r times. So this k per r minus 1 is coming here. So this is for your repeating term. The non-repeating term will have the same nature of this term, okay? Now, once this solution is with us, then again you need your initial values to find the constants. Now this situation, these two situations is actually enough to solve for yn. Y0, there is natural response or your ZSR. But sometimes we, because you see that in general, what will happen, although your roots are distinct, but your distinct root can be real and even they can be complex, isn't it? Your distinct root can be real or
Yes,
it can
sir.
be complex, but
Yes, sir.
still they are distinct. So
Yes,
this
sir.
formula is actually a general thing. The distinct and repeated root, these two can be used for any general cases. But we sometimes for simplicity of calculation, we can modify few things by using our Euler identity or other mathematical technique. You know that in our system, whatever you learn so far, in a second order system, okay, your root cannot be complex for a first order system. Can it be complex?
No, sir.
Because
No, sir.
first order system differential equation is a first order differential equation, and it will be a first order difference equation also. That will not give you multiple root. It will have a single root, but that root should be real, but it can be positive or negative. So a first order system will not have any natural frequency. Your second order, from second order ahead, your natural frequency or other things will be coming into it. Whenever we have our second order system, you see, second order system can have four possibilities, but in general, their root will be a characteristic root will be determined by a factor similar to this b square minus 4ac. Do you know this thing?
Yes, sir.
What is it? It is, for example, if we have a quadratic equation, say ax square plus bx plus c, then the general solution of this equation can be written in this way, isn't it?
Yes, sir.
But this algorithm is very ill post algorithm. It cannot be sometime used in computation.
Yes,
Not,
sir. B square minus 4ac should be greater than 0.
but if it is less than 0, still we can use computer, no problem. But other thing is there. Okay, in your numerical technique, when we start, before starting any algorithm, few things you need to know first. One is the number representation, how your numbers, floating point numbers are represented by using in computer. Second thing is how to analyze the error. We have two types of error. One is called round up error, another is truncation error. Okay.
Yes, sir.
And we have another issue called condition number of a problem. Have you heard about it?
Yes, sir.
What is it?
Sir, numbers should not be very close to each other.
Very
Ill
close.
conditioned numbers.
Do not just answer the question in a way that is intuitive but not correct. Okay. You
Yes,
try to learn. What book you followed?
sir.
What?
Chapla.
Chopra. Okay. Stephen Chopra. One of the best and widely used book. He has written two books. One is Advanced Numerical Analysis using MATLAB. Another is Numerical Analysis for Engineers. Okay, this book is written for engineers only, specifically because he's an engineer. Try to learn about condition number from that text. Okay, it is there in chapter 1.
Yes, sir.
Okay, what is condition number? This is very important in order to proceed with using computer to analyze your problem. We have our two types of problem. One type is called ill post problem. Another class is called well post problem.
Sir, we learned about one thing. If the two straight lines have very close gradient, then it is ill
That
conditioned.
means if we have two straight line, very close slope, then what will happen? They might have a solution there.
Margin of error is greater.
Okay, within that. This is one issue, but it is one of the issues. But apart from this thing, what will happen when we have our two equations or a equations or a subtraction is there in calculation, and where two numbers you have, those numbers are very small, then a situation occurs in numerical computation. That situation is called catastrophic cancellation. Have you heard about it? Catastrophic cancellation?
No, sir.
Okay, try to learn about it. Okay.
Yes, sir.
Then this algorithm is subjected to catastrophic cancellation. Then we have another algorithm instead of this you need to use to find the root of a quadratic factor. Okay. So a catastrophic, so if our problem is well posed and it is not subjected to catastrophic type cancellation, then this algorithm can be used to find the root. But the condition is that we are assuming that our problem are well post type. So in this case, that cancellation problem is not there, but still we need to identify, because the nature of the root will be determined by this factor. This factor is called discriminant. Using that discriminant, you can identify that whether the root will be going to complex or real. But still we have a nature. You see that for our system, although your roots are complex, but they have a nature. That nature is what? They have same real part, but negative imaginary part, isn't it?
Yes,
If
sir.
they have negative imaginary part, then in the complex plane, if one root is lying here, then another root will be lying in a plane that is the image of your first plane with respect to this real axis. And that we call that number and this number are conjugate to each other. Okay. So our root will be appearing as conjugate pairs.
Yes, sir.
The if your root is appearing as conjugate pairs, then what will happen? Their phase angle will be positive 1 and another negative. The magnitude will be remaining same. So that situation is described here. You can easily understand it. That if we have two roots only and they are conjugate pairs, then what will happen? one root can be represented in this way in exponential form, the other root will be this. Then if we have these two roots, they are distinct. Although some mathematical similarity is there, but still they are not the same root, they are distinct. So you can use your distinct formula to find your root. We have our two root, then two constant will be involved. This is your lambda 1, this is your lambda 2. So your lambda 1 is gamma 1. Gamma 1 is equal to magnitude of gamma e to the power j beta, and your gamma 2 is equal to magnitude of gamma e to the power minus j beta. They are conjugate to each other. So your general solution will be this. Then you put your thing there, you will be obtaining this thing. By using simple trigonometry, we can arrive in this equation. So you see that in this equation of classical form, you have your two unknown constants, C1 and C2. But your signal is real. Then what must be the nature of this constant?
So real.
Real. If they are real, then complex term will not be there. A complex term will not be cancelled. It is very simple, okay? You can easily examine that your C1 and C2 will have this nature. They will be conjugate to each other.
Yes, sir.
Otherwise, because if these two terms are not conjugate, then this cannot be real, because two complex number, when you add two complex number, this is complex, but your result is it not, the result is not real?
Yes, sir.
Because if you add two conjugate numbers, then the result will be
Real.
2 of the real part. This must be equal to twice of the z real,
Yes, sir.
because imaginary part will be cancelled.
Yes, sir.
So a real signal, we have our yn, that is real, but mathematically some complex constants are associated with them. Then what it signifies, that means these two parts of the solution must be conjugate to each other. Otherwise, a real signal cannot be what? Can you generate a real signal?
No, sir.
For this reason, okay, in your Fourier analysis, how many forms of Fourier series you have studied?
Sir,
How many forms?
two forms.
2 forms. Okay, good. One form is
Real.
real. Another form is
Complex.
complex. For example, this is the way we explain or we express it in mathematics. We call that one form is trigonometric, where cos theta, sin theta are involved.
Yes, sir. Yes.
This is real. And we have another form that is called exponential form. And your exponential forms is complex
Yes,
for
sir.
the same signal. If we have a same signal, but real Fourier series is real, but if we use exponential term, it becomes complex. That signifies that the Fourier constants, for example, if we put this is your frequency, this is your Fourier constants, then what will happen in the case of trigonometric series? All the constant will be there in the positive side, real part. But in the case of complex, you will see that some are appearing in the real side. Exactly a similar constant will be there in the opposite side with minus frequency. That minus frequency has no significance physically, but still we need it. The reason is that when we are using complex form, then these two would be needed in order to cancel the imaginary part of your solution. So
Yes, sir.
the constant will be appearing there as conjugate pairs. Half will be in positive side, and that's why the spectrum will be symmetric with respect to the omega equal to 0 axis. I don't know to what extent you explore it, but we will revisit it with great detail in this course also. Fine. Then having this thing with us, what we can do then? After having your differential equation known, first step is what? Say this is your differential equation, you know it. Okay, we know that the order is 2. Then our highest operator will be E2. Then we write this equation in operator form. This is what that form. This is your input side. This is your output side. So your QE equal to what? Your QE equal to E2 minus 0.6E minus 0.16. And your PE equal to what? P equal to simple E2, isn't it?
Yes, sir.
Then our next step is what? We write our equation, okay? Our equation will be gamma square plus 0.6 gamma plus 0.16. This is what that characteristic equation, set it equal to 0. This is what the characteristic equation of our difference equation. Now you have to factorize it to solve your for your gamma. You have two values of gamma, and one is 0.2, another is 0.8. So the roots are distinct or equal. They are distinct, isn't it? Are not they?
Yes, sir.
If they are distinct, then this is what the general solution for y0k. Two constant will be involved. The next step is what? We have to find C1 by C and C2. If we want to find y0k completely, then that y0k would be equal to yzir, isn't it?
Yes, sir.
So at this stage, if we apply the initial conditions given there, y minus 1 equal to 0, y minus 2 equal to this, then that will give you the value of your ZSR. Okay, so in this equation, you put the value of k equal to minus 1 and equate it equal to 0. Put the value k equal to minus 2, equate it with 25 divided by 4. Then you solve these two equations simultaneously to find the value of C1 and C2. Is your system stable?
Yes, sir.
How did you identify?
The value is between 0 to 1.
The value of our characteristic root between
0 to 1.
very good. So for a real system, this must be the case. Okay. Now this same thing has been illustrated here by putting you initial values. C1 is obtained as 1 divided by 5, C2 equal to 4 by 5. Then this is the solution. You see that you can also solve the problem by iterative technique. And we have solved this equation. Then you can compare that these two solutions are same. Okay, you can verify it as a practice of your MATLAB exercise. Okay. Are you doing programming in MATLAB?
Yes, sir. Right now we are doing MATLAB every day, sir.
Or every day? Then you can solve this problem there as an experiment. Okay.
Yes, sir. From the previous semester, we have been doing a lot of MATLAB.
Okay. Now consider another example. I did not write the equation, differential equation, but we started from characteristic equation. Okay. So in this case, you see our characteristic equation will be equal to what? Your QE equal to this, isn't it?
Yes, sir.
And just from your key, you can easily directly write your characteristic equation will be equal to lambda square, gamma square minus 0.1.56 gamma plus 0.8 equal to this, isn't it? And you can easily identify that in this case, our root will be equal to what? Gamma is equal to 1.56 plus minus square root of 1.56 squared minus 4 into 0.82, isn't it?
Yes, sir.
Divided by
2a.
That you can easily identify that your discriminant is negative, isn't it?
Yes, sir.
So your roots are complex conjugate type.
Yes, sir.
Okay, it will have a real part equal to this one. It will have a real part 1.56 divided by 2, isn't it? And the
Yes, sir.
imaginary part will be determined by the square root of these quantities. So your root will be one root will be equal to what? 1 root lambda 1 will be equal to 0.78 plus j 0.45. Another root will be equal to what? 0.78 minus j 0.45. Are not they?
Yes, sir.
So these are the two roots. Then if we have our two root, you can directly put that two root to that equation. Okay, so your y0k is simply equal to C1 into gamma 1 to the power n plus C2 into gamma 2 to the power n. Okay, you put your gamma 1, gamma 2 there directly, you will obtain your yk and simplify it. Okay, or you know the formula for this particular two complex, a pair of complex root, you can directly use this. You can directly use this. Okay, in your solution, it was a constant. This was the magnitude of gamma, and this quantity is the phase angle of gamma, and k is that your sample variable, theta is the angle. What angle? Theta is the angle that you do not know yet, because theta will depend on C. So in this case, how many unknowns now? In this equation, you have two unknowns, C1 and C2. But when we put into trigonometrical form, still you have your two unknown. One will be C, another will be
Theta.
theta. So you put your initial values there, then your equation will be something like this. You solve for C and theta. Okay, in whatever ways you need to go, this is your choice. But you need to practice if you want to get some idea about it. Okay, pick up some problem from your book and try to get accustomed to the process. This solution is very simple. Even in my slides, probably somewhere you will find that we tune the variable R of a circuit at one stage. Your circuit will be giving you what we call this type of output. Okay, then this output is categorized in which form? Is it uh, underdamped, or it is overdamped, or undamped?
Sir, under them.
This is underdamped. The reason is it
Too
has
complex.
it has a damping factor, because complex conjugate root will always give, okay, yeah. Although in our case, the root negative real part is not the matter, but what it matters is that the real part should be less than 1, isn't it?
Yes, sir.
Okay. So in this case, you see it is less than 1. As it is less than 1 for any value of k, this quantity 0.09 to the power k cannot be greater than 1. Okay.
Yes, sir.
Now, this is what the last thing that I will discuss today. Okay, so we have, okay, now we have another thing left uh, about particular solution, okay, that we will discuss later. Probably this is the last class before mid-exam. So your thing will be up to this point before mid. After mid, we'll just discuss about this issue, then we will switch to our transform technique, inshallah. Now the thing is that that if we want to use the technique that we usually follow for our signals and systems, that our response of our system YK will have two parts. One is our YZSR. The way already you know that how it can be determined, and we have our ZIR. That ZIR depends on the input K. That because this is this No. It is reverse. We have our y, z, I, r that we have determined, zero input, okay? The zero input response we determine, but in order to find your YZSR, by using classical technique, we need to again solve the differential equation or difference equation. But we have another technique. Can you tell me what is that technique to find ZSR? If the impulse response is known to us?
Sorry, integration.
Integration. In your discrete time system, it is?
Summation.
What is that summation? Name of the summation is what? Is it not the convolution of your impulse response with your input,
Yes,
xk?
sir.
Or in this notation, your xk can be fk, okay? Same input. That means if your impulse response is known, then you convolute your impulse response with the input, that will give you YZSR. Thus, in order to do that, like your continuous time case, you have to determine the impulse response of a discrete time system. How to do that? We have two ways to do that. One, we can calculate it recursively, or we can calculate it in a closed form. But the idea is very simple. Your idea is what? That will come from the general equation of your difference equation, general form of your difference equation. Okay, just hold a minute, please. Okay. Then our technique is what? To find the impulse response, your input should be replaced by an impulse, isn't it?
Yes, sir.
So if this is your input-output relationship in operator form, if this is the input-output relationship in the operator form, then if we replace our fk, the input, as delta k, you know that delta k has a magnitude equal to 1 at k equal to 0. Then that output y, we can call it the impulse response hk. So this is what this equation, okay?
Yes,
That
sir.
if we replace our input by delta k, then your output will be equal to this, and the initial for a causal system for negative values of n, this would be equal to 0. If we have this thing with us, then using a difference equation that is available, you can proceed with calculating the impulse response. Okay, let me erase these lines. Okay, fine. Now, can you see this thing? Say this is your equation, okay? Input output equation. If we want to find the impulse response, how can you do that? You replace your fk by delta, okay?
Yes, sir.
Fk by delta. Then your output yk will be hk. Our objective is what? We have to solve for hk, isn't it?
Yes, sir.
Now, if this equation is available, what you can do, you can solve it recursively in this way. Okay, what is the value of, actually you see, you know that our variable is k, and equivalently n in your Huygens book. So this is your delta k. Your delta k is appearing at k equal to 0 with magnitude equal to 1, isn't it?
Yes, sir.
So do we have any value elsewhere?
No, sir.
No. If no value is there, then we can rearrange this equation, for example, to rewrite as Sk equal to what? Your Sk equal to 5 delta K plus 0.6 Hk minus 1 minus plus 0.16 Hk minus 2. Okay. Then you find your H0. H0 equal to what? H0 equal to 5 delta 0 plus say 0.6 into H minus 1 plus 0.16 into H minus 2, isn't it?
Yes, sir.
Your initial value where for H was given that for negative index it is 0. So this is 0, this is 0, and delta 0 equal to what? Is it not equal to 1?
Yes, sir.
So your H0 equal to what then? H0 equal to 5.
5.
So your H0 equal to 5. Next thing is what? You have to calculate H1. H1 equal to what? H1 would be equal to 5 delta 1. Although I am writing the thing, but no meaning of this thing actually physically. It is equal to 0.680 plus 0.16 H minus 1.
Yes, sir.
So what is the value of delta 1? Delta minus 1? Is there any value for K equal to 1?
No, sir.
Of delta? No. So this is 5 into 0, 0. And we don't have this value actually 0.16 into 0. Then we have a value 0.6 that we calculated from earlier state 5. Then your H1 would be equal to what? H1 would be equal to 3, isn't it?
Yes, sir.
So if your H1 is 3, how about your H2? H2 equal to what? H2 equal to, because your input term will be always 0, then this will be equal to 0.6 into H1 plus 0.16 into what? H0, isn't it?
Yes, sir.
And this is equal to what? 0.6 into 3 plus 0.16 into 5. Okay, you can easily calculate what will be the value. In this way, you can keep going in calculating it and plot. Okay, then you will find the value of H. Now the question is, how long you have to calculate? How far you have to go? This is the question, isn't it?
Yes, sir.
If you see that after few turns, it is going to the steady state type solution, that you need not to move further, okay? But if it keeps going on increasing it, then it becomes unstable. For an unstable system, no closed form of solution is obtainable, okay? Or meaningful. So see, in this way you can go to find your impulse response, or you can use your generalized technique to find the impulse response. Okay, that generalized technique is this. And I hope that you can remember a similar equation you have seen for the case of continuous time. It was, for the case of continuous time, it was Bn delta K plus Pd Ynt Ut. Can you remember?
Yes, sir.
This was your St. So in the same way, it is written in this form. And if your B0 A0 will be coming from the difference equation, and Y0 N is Ynk is the natural solution, will have the form Ynk will have the same form of Y0K, equal to, say, for distinct root C1 into gamma to the power K plus C2 into gamma to the power, say, K, or it can be, if it is complex, it can be cosine or sine, something like this. So once this is determined, then you have to apply your initial values there to find C1 and C2. Then this should be applied here in this equation to find your the value of your delta K. But we have another transform technique in solving this thing, like Laplace transform, we call it Z transform, and this will be the central constraint of your forthcoming course of digital signal processing. So this same by using same technique, we obtain this solution. Oh, sorry. We obtain this solution. Then once this solution is obtained, then we put the value there just to find the value of y and k. Once your y and k is available, then your sk can be written because your b0 was equal to 0. So delta term is not present here. Now our general solution will take this form. uk means this is for k equal to 0 ahead. Then we have our two values given there in earlier examples, H0 and H1. These two values can be used to obtain two equations from 9.38. These two equations can be solved to find the value of C1 and C2, because you need to know at least two values of your SK to find the value C1 and C2, isn't it?
Yes, sir.
From where that can be done? From your earlier equation of from your input output relationship, this relationship, okay, from your input output relationship, you replace your input by delta k, then you obtain two values of hk. That two values of hk can be used there to find the general form of hk, the impulse response of this particular problem. But if you have another problem, you have to follow the same underlying technique. Now I am taking your percentage. Although I was